Welcome back. In this lecture, we will discuss how channel estimation can be done for wireless systems using deep learning models. I refer to some of my previous videos, lecture number 5, where I introduced deep learning and machine learning models. A basic Python demo was given, then I integrated machine learning with deep learning for basic squaring operation and channel estimation basics also I have discussed. So in this lecture, I'm going to club all this and I'm going to uh, explain how channel estimation can be done using deep learning model, and then I will synthesize my own data, and then we will do the channel estimation on Python. So do watch the complete lecture to get understanding of how this can be done. Wireless transmission I have discussed many times is consisting of reflection, diffraction, scattering. So everything is very complex here, and signal that reaches wirelessly suffers a lot of attenuation and phase shifting, and therefore the channel model is given by a change of an attenuating factor and delay, a group delay. So this I have discussed in detail in my first few videos. You can latch on to those videos. And basically a narrow band approximation of the channel is given, that we write it as a summation of n multipath components. Basically this is multipath propagation. AI is the amplitude of each component and tau y is the delay with which each component reaches the receiver. So once this is done, we want to estimate the channel using pilot channel estimation, which means that we set first of all a known reference signals. So we know what is x, what is y, what is h, and data streams. We insert the pilot signal, and the receiver compares these known pilots to what it receives to estimate it and estimate how the wireless channel distorted the signal. And this allows for equalization. Equalization is basically multiplying with inverse of the channel's transfer function. So suppose that x is the modulated signal, h is the fading coefficient, n is the AWG, and then the received signal is given by x h plus n. है ना? So basically this we have discussed many times, that if a wireless user tries to communicate with a receiver, if the signal is traveling on the wireless path, what happens is that your user sends first of all a pilot signal over a fading channel of h in the presence of AWG and identified Gaussian noise n, which is random, h is also random, y is received. So basically y is equal to x h plus n. While estimating the channel, we don't have the information about noise. So we first of all, in the pilot transmission, we know what all these are, and based on this we want to estimate h. The channel is h, so we want to estimate h. If I neglect this, this basically becomes y is equal to x into h hat, because now h hat represents the predicted value of the channel, and therefore h hat in simplest form is y upon x. This is actually a channel estimation algorithm that I discussed before. But in this lecture, what we are going to do is to predict using deep learning model. Of course, if h is not equal to h hat, because we are not considering the noise, it's going to be an estimation error. Is the difference between the actual and the predicted value of the channel. The machine learning basically are different from traditional deep learning, traditional computers or calculators, in which the computer give the data, the input, we give the program on which the function which is going to map the input to output, and we evaluate the output. While in this machine learning or deep learning, machine learning subset is deep learning. So basically, what happens is that the computer is given a set of input and output, and the computer identifies what is the function that has mapped the input and the output. So basically, these are features and these are labels. So features are inputs and outputs are labels. But now in machine learning, basically the features and the labels are given, and we try to map or find the function that maps these two. So in our case, I'm going to implement a deep neural network, and which consists of multiple hidden layers. The features for us will be the modulated symbols x and the received signal y. है ना? So what is received y and what was given x, and what is the thing that is relating these two, the noise and h. So we will give labels as the noise vectors, channel fading coefficients h. So basically, when this deep learning model we want to train, we'll want to increase these features and labels. So not only two features we'll use multiple, and for that, what we will do, we will make it complex, है ना? Complex x and y. So doing that, the x can be written in rectangular and polar form. Rectangular is a plus jb, where a is the real part and b is the imaginary part, while the polar coordinate system says that the Magnitude is root under a square plus b square, and the phase is tan inverse b upon a. So I am going to use the rectangular format. You can use either. We just want to increase the features from the same labeling. So we'll use real part of x. We'll denote it x underscore real. We'll use imaginary part of x, x underscore imaginary. These are the symbols. I'm going to use QPSK modulation while I demonstrate. So I'm going to use quadrature phase shift keying modulation, in which every symbol is 90 degree away from each other, which means the complete 360 degree is divided into four symbols, and each symbol is 90 degree apart, basically 360 by 4. The labels also will become, you will understand it, they will become, and I will demonstrate later on also, that they will become a combination of real and imaginary parts, because x is real and imaginary. We'll also take noise to be complex Gaussian. So basically now we have four features, because x is the QPSK is also complex, y is going to be complex, and I'm taking, just trying to simplify this, I'm taking h to be a simple thing, right? The fading coefficients will be simple. I will assume Nakagami M distribution in this demonstration. So after training we estimate h, and that happens to be h hat. How do we train the deep learning model? We first of all import all the libraries. We import a data set, and where we have features: x real, x imaginary, y real, y imaginary. All those four are features, and h is the labels. We perform pre-processing. We will make it into 0 to 1. We'll first of all minimax scalar we'll use, and we'll bring everything between 0 to 1, and then start. We'll define the deep learning model. How many hidden layers are there? What is the input dimension? The input dimension is going to be 4, right? Because 4 features are there. The output dimension is going to be 1. We'll compile and train the model, and we'll predict, and we'll perform some evaluation of the model. This is how any deep learning model can be trained and evaluated. What are the Python libraries that we use? We use NumPy arrays. We'll use pandas. We'll use standard scalar, minimax scalar. We'll import sequential model, dense model. We'll use plotting also. So that is PLD. The training data set that is here is basically like this, right? We'll have x real, x imaginary, y real, y imaginary, and you can understand that x real and x imaginary is basically 1 upon root 2 plus minus 1 upon root 2 plus minus j times of 1 upon root 2, and 4 combinations of each. So therefore this is going to be like this. This is the QPSK symbols. We have noise, but noise is not known to the system. That is what we are doing. We are estimating h without knowing the noise. So these four are going to be my features. So I will, my input data will be x underscore real, y x underscore imaginary, y underscore real, y underscore imaginary. These are the four features, and the labels are like this. So how I import that in Python? Just quickly, we'll show the complete code also. We'll use like read underscore CSV for the file where we will store this. We'll use columns under this name, and doing that, what we'll have is these four features. And you can also use 0 1 2 3 for indexing. This is 0, this is 1, this is 2, this is 3. This is very simple. And we'll another will another have data frame df3, which will store the labels, which is the fourth indices: 0 1 2 3 4, fourth indices. That is the channel estimation. So basically this df3 and its value becomes the labels, and df2 or df1, either when you can use. I use df2. Both will be the same thing. They are importing the same values for the sheet CSV file. So basically the features are coming from df2, which have these four basically things: x real, x imaginary, y real, y imaginary, while the labels are df3 dot values. So once we do that, what we'll do, we'll define the sequential model, sequential deep learning model. I will use first of all input dimension of 4, because 4 features are there, and the activation function. Firstly, I will use ReLU. I will use all the activations to be ReLU in each layer. The output of the first input to the first is 4, and output is 64. So we'll go one by one. The hidden layer 1 has 64 neurons as inputs. Uh, Hidden layer 2 will have 32 neurons. Hidden layer 3 will have 16 layers. You can, and each will have activation functions of ReLU. And how many outputs we have? How many labels we have? We have only one label, and CSI, the H. So therefore, we will have dense one. Once we have this, what we will do? We will compile the models. We'll use, this is the model's name. We could use any name here. So this is what is using model.compile. Using an Adam optimization, loss of MSE, and metric of mean average error. This all we will show in Python also in this lecture. And also we will then fit the model on the data. So basically we will have x scaled and y scaled are the scaled values of the levels and features. Basically I'm going to use minimum x scaler in the code because the deep learning model cannot understand on the complete data. It's going to only understand when you bring everything into one roof that is 0 to 1. We use I will also discuss how number of epochs can be changed. So let us firstly go and generate a data set. Once we generate the data set, then we will implement the Python implementation of the same to see how this is done. Let's go. So first of all, let us generate our own data set. I am trying to generate 5,000 samples. I am trying to generate using Nakagami M. So Nakagami M has two things. First of all, uh, the shaping parameter M and the scaling parameter omega. So I am taking M is equal to 1.5 and omega is equal to 1. I'm taking variance sigma is equal to zero point 0.1. Just to make regeneration more accurate, I am defaulting 42 random number generator so that every time the code is uh, invoked, we get the same random variable. Now I am trying to generate first of all a QPSK modulated X. So for this, you know that QPSK is basically 90-degree phase shift in four symbols. So the four symbols are 1 plus j, 1 minus j, minus 1 plus j, minus 1 minus j upon square root of 2 to make it of unit uh, power. So for this, the constellation is basically my X. Now this constellation, basically what I am trying to do here is that I am trying to make it a constellation of x real and x imaginary. So I am firstly trying x as constellation. So and symbol index is basically 0 to 4 of size n. So I am generating 5,000 samples and I am trying to extract the real and imaginary parts because these are in rectangular form. So all four are basically can be represented in polar with plus minus 90-degree phase shift, or it can be represented in rectangular from a plus jb. So I'm trying to do the real and imaginary part. So my x is basically now x real and x imaginary. I also now require this Nakagami random variable. So I will use in Python rng.gamma. So it generates gamma random variables. The square of Nakagami is gamma basically. And the shaping parameters and scaling parameters are m and omega m by m of size 5,000, right? So this is my z. And what is h? H is basically square root of z. So this h becomes my channel which I'm going to now estimate. Now I will also generate the AWGN noise, so noise real, noise imaginary, which will follow Gaussian distribution denoted by normal distribution having mean of 0 and variance sigma, which I declared zero point 0.1 of size 5,000. So I also add them in rectangular form. My noise becomes noise underscore real plus noise underscore imaginary times 1j, which means it's the imaginary part. Now, what is my received signal? The received signal is basically h into x plus noise. So I do that. I have already generated h. I have already generated x. So I will do that. And of course, this noise is also basically complex number. So y will automatically become complex because x is complex, noise is complex. You will get y which is complex. So again, I will bifurcate into its real and imaginary parts. Y underscore real is basically the real portion and y underscore imaginary is the imaginary part of it. And I am now trying to generate a data frame to store all these values: x real, x imaginary, y real, y imaginary, the channel and the noise. And I save that into a QPSK Nakagami underscore data dot csv. So in this manner, I can download this file. So if I run this file, right, it's running and I get this file. Let us see what happens in this file also. So in this file, these are the values that I have generated, only 5,000 of them. So regularization will be required in this. Otherwise, you need to generate a larger data set. But basically, my columns are x real, x imaginary, y real, y imaginary, h, and noise. You can also verify that like what is happening, that x real is getting multiplied by uh, h, and what is getting added? Noise. But in this case, the noise is basically 0.2360. So I will use 0.2360. This is the real part only. So what I will get? I will basically get the y real portion here. So you can understand that x multiplied by h plus noise is basically y. This can be verified for all the values. I can also bifurcate noise into this. And to our model, this will not be available. And this thing will not be available. What we give to our model is x real, x imaginary, y real, y imaginary. This is what we give, and we want to predict this. So this will be the next thing that we will try to estimate these using deep, deep learning. So now we will perform the action of channel estimation in Python using Colab. Uh, First of all, we will import the basic libraries NPy, NumPy for mathematical operations, pandas, pre-processing, uh, TensorFlow, sequential mod, uh, dense layers, gamma, and PLT for plot. Then we will import our dataset. So our dataset we can import using, first of all, remember that we saved it using the name QPSK Nakagami uh, underscore data, so that I have uploaded in this folder. So I can actually use this line df1 is equal to pd dot read underscore csv. This will read the csv file uploaded in this folder named qpsk underscore gamma nakagami underscore data dot csv, and it will use all the columns as x underscore real, x underscore imaginary, y underscore real, and y underscore imaginary. Rather, I will do this which is more favorable, that I will import it like this. I will use columns indices 0, 1, 2, 3. So the starting point is 0. The 0 is the first column. Therefore, I will import the first four columns as df2 and import the fourth number indices, which means the fifth column as df3. So basically, my df2 is basically df2 dot values. If I do, I will store those to be the features. The features are basically x real, x imaginary, y real, and y imaginary, and the labels are basically df3, which are the channel estimates. So if I can just run this part, right? So basically now my df1, df2, df3 will have, df2 will have the four features, and df3 will have the channel csi values. Now we'll perform pre-processing because the values are very random right now. So we'll perform scalar as minimax scalar. So between 0 to 1 we will make all the values. So I will take x scaled to be features scalar dot fit underscore transform. So this basically pre-processes the data. X scaled is basically all the four features now scaled between 0 to 1, and similarly y scaled is also between 0 to 1. Remember that we have taken 5,000 values in data generation, so that will be the case. Now we'll define our deep learning models. I'm using basic deep learning model, the sequential model. The input dimension will be 4 because this is most important thing. The 4 corresponds to the 4 features that we have. The output of the first layer goes to the hidden layer having 64 units, then 32 units, then 16 unit, and final output has to be the edge predicted, which is dense layer output having one neuron. Intermediate activations are ReLU functions that I am using. So this will perform. So if we can just up to this point, if we can execute, everything is okay. It seems right. So this is okay. Now what we will perform? We'll perform the action of compiling the model. For compiling, we'll use this line model.compile. The optimizer is going to be Adam. Mean squared error is going to be our loss function, and mean average error is basically the metric. So if I can again run this direction, this is also fine, and we'll also record the history for which we'll fit it over underscore scale, y underscore scale for 10 epochs, batch size of 50. Batch size of 50 means I am having 5,000 values and 50. So we are basically having 500 different, sorry, 100 different batches, 100 different batches over which 10 epochs I am just trying to do. And I am splitting for validation to be 0.1, and verbose 1 means it will be displayed. So I'm going to run this. It will take some time. So it's going to fit on x scaled and y scaled. You can see the progress. The number of epochs is going right. So basically, this has happened. I will also now try to do it for 100 epochs first. We'll do it for 100 epochs basically, and then we'll see what's the output. I will till then explain the further lines also. Like this is we are subplotting basically the history, the value of loss. So the loss that is being incurred here between the actual and the predicted value will be plotted against the epochs. Epochs is the number of iterations that a deep learning model is going through, And what I am trying to do now is predicted data. So predicted data is basically the model that is being trained for 100 epochs right now. Dot predict means we are predicting using this model, and over the x underscore scale. These are the four features which are scaled. So predicted data is also going to be scaled. So what we now need to perform is inverse transformation. We want to make the data set back, and what we gave to the system is h, and what we wanted is h hat. So our h is basically the original data recovered, which is inverse underscore transform over the y scale. Remember, y scale is the labels, and predicted underscore data underscore back is basically inverse transform of the predicted data. This is the predicted data. We predicted using x underscore scaled, but this output will be also scaled. We want to unscale it to actual values, and then we will again try to save it into data frames. So original data that is recovered, that is y underscore scaled inverse transformed, and predicted data back to x actual and x predicted. I'm now trying to save it to predicted underscore data dot csv, because it's very convenient to see what happens to data in csv files, and I will download it. So this predicted underscore data, you have seen that the iterations 100 have been done, and this is what we are getting. So this is my file predicted underscore data. Now if you can see here, this first column is basically H actual, which was the actual data set, the actual channel estimate outputs. And this is what we are getting as the, so as the predicted value from the deep learning model. We have used only 3 hidden layers, and we have used only 100 epochs of batch size 50. You can increase the epochs or you can reduce the batch size. If you reduce the batch size, each epoch will take more time, but that will give you more accuracy. So you can see that it's 0.73, it's 0.88, 1.21, 1.14, 0.67, 0.71. So it is highly random, but a deep learning model is also becoming that random. You can see all those values, right? So if you just and I have taken it only for right now 100 epochs. So if I can just, you can do this. You can see the error is, is very less, and you can see, you can check for yourself. If you reduce the batch size, it will take more time. Like if 50 is made here, it is 50, and if this 50 batch size is made to suppose 10, like this, if you make this 10, and if you run for 100 epochs, your accuracy will increase enormously. It will take more time because now 10 means it is going to be 5000 upon 10, 500 different batches that are going to be processed. Or you can leave it to 50 and you can make this 1000. So it will be 1000 iterations. Like, and this time it is, you can see it's the epochs are 100, so it will become 1000, and you can see that the loss is, loss is decreasing. So it will stabilize. The mean square error and all these are being displayed. So this is the manner in which I can take my own data set, I can put it as features and labels, and I can perform deep learning based channel estimation in Python. You can use different models, deep learning models, LSTM, RNN, whatnot, and you can have different modulation schemes, noise vectors, and you can change the features and labels to enhance the contribution in research if you want to publish papers using deep learning in wireless communication system. Hope this lecture has helped you in some way. Thank you very much.